So we've talked about graphing, transforming, and then using some exponential functions, just plugging in to get what we want. Remember the investments and interest rates and things of that nature. Today we're going to talk about actually solving these by hand. Remember the exponential functions are any function where we have a base and then there is a variable in the exponent. Remember, it's not just the existence of an exponent, it's a exponent that has a variable in it. And then we also know we've been dealing with that general function, the general family function here, which is a to the bx, where a is going to be where it crosses the y-axis, and then b is the rate of change that we're going to see, the ratio that we will see. All right, we're going to start off with some nice easy ones, but before we do that, I'm going to take a look at a sheet that I've given you here, right there. This is a little exponential rule we will use, and you have used almost all of these exponential rules at some point. But we're going to highlight a few of these. You know, these are the exponential rules that we know. When we're multiplying them, we add those up. When we're dividing, we subtract, so on and so forth. The focus that I want to put on today, though, is these rules right here, specifically the negative rules. The negative rules, we will need those. And if you'll notice here, there's that zero rule, any number to a power, zero power is 1. But this is what our focus is going to be here today, is the negative exponents. Now, a negative exponent, never changes the sign. What it does is it makes the inverse of a number, and that is actually how you write the inverse, is you put x to any number to a negative x power, and you get the inverse. But when you see an inverse, what you need to think about, or negative power, what you need to think is an inverse. So if I have -2 to a -1 power, that is not -2. What that is saying is 1 over 2. That is the inverse of that number. If that number is already a fraction, let's just say we had 2/3 to a -1 power, and we're going to stick with the -1 for right now. We are going to the inverse of that, and the inverse of 2/3 is 3/2. There is not a change of sign. Matter of fact, if the number is already negative, let's say we just had the number -1/5, and we are going to take it to a -1 power. We are going to have a flip, so it's not going to be 1 over 5, excuse me, it's going to be 5 over 1, and it will retain its negative sign. So when you see that negative exponent, think about relocating numerator and denominator. And remember, this 2 did have an understood 1 denominator. So that's what we're going to look at today. And then we got a little example here. And you would perform the power afterwards. Like in this case, let's say we had a number such as, let's just say, keep it easy, 1/2 to a -2 power. First thing I like to do is flip it. So, and then I can drop the negative sign. The inverse of 1/2 is 2. So the negative sign that was attached to our exponent is now gone. So now that that exponent is gone, we just have a 2. Once you perform the duty of the negative sign, it goes away. Don't keep it there. So this would be 4. And you can always check your work. If you were to put this in your calculator, 1/2 to a -2 power, you're going to get 4. But remember, that negative power equals a reciprocal or an inverse. It's going to be a flip of anything that it touches. It doesn't flip everything, it just flips the parentheses that it is touching. All right, so we will need to know that rule as we're working through today's lesson. Now, we are going, there it is. There's our rule. Like I said, start a little easier here. Here is what the rule with exponentials is. And today we're going to either have a common base or we're going to get a common base. So this one, nice and easy, they've given us a common base. Now, if two numbers have the same base and they are equal to one another, that means their exponents have to be equal as well. So if we have this, what we can do is when we have a common base, we can cancel this out and then just set up an equation with everything that we have left. 3v equals v plus 2. Now we're down to just a linear equation. So we subtract v from both sides, so we end up with 2v equals 2. We would then divide by 2, and v would equal 1. You could go back and plug in that answer and see if that works. If we have 2 times 2 to the 3 times 1 power, well, that's going to be 2 to the 3rd power. And then the other side would be 2 to the 1 plus 2 power, which is 2 to the 3rd power. And 2 to the 3rd power is 8, and of course 8 equals 8. So we can check our answers there. You can also graph these and see where they cross one another. Usually, especially if they have a common base, that takes more time. And not to mention, if you get an irrational answer, it's going to be really hard to find that. All right, let's take a look at another thing of the lesson there. Another one with a nice, friendly, common base. I'm going to pause it and let you get a head start on me on this, and then we'll get working. So we should recognize that the 5s are the common base, so they can go away, leaving us with negative b minus 2 equal to 3b minus 2. And at this point, it's just a matter of how you like to solve a linear equation. I like to pull the smaller variable to the larger one. That would be moving the b to the 3b, which makes 4b. And in the same line, I'm going to go back and move the 2 to join the other 2. Before you start thinking, well, 0 is not a problem. 0 is actually really easy to work with. Now I've got my skepticism as well anytime I get a 0, but we can check in our answers and see. So what we learn is b is equal to 0. Well, let's see if that's the case. We go back up to the top, we'd have 0 minus 2, well, that's negative 2. And then we would have 3 times 0, which is 0, minus 2, so that actually does work. I'm like you, though. Anytime I get a 0, I always get a little reluctant to use a 0, but in this case, it actually was 0. So when we have a common base, that's all that is to it. You're not actually going to see any of those today. We should be able to do those. The trick comes in when the bases are not common. So we're going to start with a few where you can recognize probably what the power is, and then we will talk about some where they're very difficult to find. So here we go. So we have these two, 64 and 2. So a good place to look is whatever the smaller number is. If I have 4 to some power, does it equal 64? And then you can go into your calculator and plug these in and see if it actually works. So when we do this, I could say, well, 4 to some power equals 64. We're going to learn how to use logarithms later, but you can just go down the list. Just on your calculator, go 4 times 4. Well, then that would be 16 times 4 is 64. So there are 3 4s right there. Another way you can do this, some students are really good with factoring trees. You can break down a factoring tree and see if there's a common base. I don't really like this one because a lot of times I overshoot what the number actually was. But whatever method you use, that's what we do. So here's what we're going to do. We're going to take our 64 and change it into 64, but with a different base, like we just decided. 4 to the 3rd power does equal 64. So this 64 here is going to be replaced with 4 to the 3rd power. You can put it in parentheses just like that. That's fine. Can look like that. Now you'll learn later on that, hey, I'd rather just put the 3 on the outside. Well, you can do that. But just for simplicity's sake, we're going to make it look like that. So this would be 4 squared. So now we do have a common base. This is 4 to the 3 x plus 2. Notice the parentheses stayed there with it. And then 4 squared. Don't worry about all the stuff that's going on in the exponent just yet. You've got a common base, which is what you were wanting. So my 4's are going to cancel. This is going to leave me with 3 times x plus 2 equals 2. Distribution. I guess you could have technically divided by 3. That's sometimes a good move, but in this case I don't like it because it would give me a fraction right off the bat, and I would like to avoid the fraction as long as I can, whenever possible, which in this case it is. I will subtract the 6. And like I said, we had an unavoidable fraction, but at least we weren't sitting there moving along with it, so that's negative 4. And then lastly, we divide by 3. So the x value in which these two equations are equal is at x equal to negative 4/3. Let's do another one where we can use some mental math and get it. Negative 1. So like I said, we were going to have some negatives going in our way. Now let me just say this. When you're comparing a fraction to an integer, the negative exponent is going to be in your future. Now there's actually 2 ways of doing this. I'm going to write this one over and show you this, because these two numbers are actually inverses of one another. You can give the negative 1 power to either one. Here's what I'm trying to say. We have to get a common base. So in this case, I want to make a common base of 2 on the left side, and I want to make a base of 1/2 on the right side. So I'm working the same question twice. So what I can do here is, when I need to change 1/2 to 2, all I have to do is make it 2 to the negative 1 power. That is that rule that we should power. So this is 2 to a negative 1 power. And then we still have our 2 minus a as an exponent as well. And the other side, we just have a 2 squared. So we have a common base. We can wipe those bases out. Once we've wiped those bases out, we have negative 1 times 2 minus a equals 2. In this case, instead of distributing negative 1, I'm actually going to divide by negative 1. Only have to do that one time. I would have to distribute twice and then move it over anyway, so why not just divide by that? So that gives me negative 2. I move my 2 over to join this one, and I'm left with negative a equals negative 4. If negative a equals negative 4, then positive a equals positive 4. Now let me show you what I was talking about just a moment ago. I'm going to do the same thing. Don't think that this is a different question. It's the same question, it's just a different method. Instead of changing the 1/2 though, I'm going to change the 2. And if you're wondering, well, how do you know which one to do? Whichever one you choose. So 2 is also 1/2 to a negative 1 power. So I've changed the 2 to 1/2 to a negative 1 power. Well, what's the difference? Well, there is no difference. We're going to be dealing with the negative signs on the other side, but it's really the same thing. So we end up with 2 minus a equals negative 2. Sounds familiar, right? Same exact thing. Going to move the 2 over to join the negative 2. So now I'm stuck with negative a equals negative 4. So therefore a equals positive 4. 2 ways of doing the same thing. All right, now the tricky part. These are the ones you're going to see. If you go to Delta Math, this is the first question on your Delta Math. Now, your Delta Math is not going to have all these crazy numbers, but I chose to do these crazy numbers. So here's what I'm going to do. I'm going to show you a video. You see it right here. There's a video right here, and I'm going to put this on the other screen if you want to go back and look at it so you don't have to go through this entire video. So I'm going to play this video here, a little bigger here, and I'm going to show you how to find a common base with your graphing calculator. Here we go. What we're trying to find here is a common base between the number 7,776 and 216. Obviously, we can't do this in our head, but what we can do is let Desmos and a table show us what we can do. So watch how this works. I'm going to go to my first one here. You can look at the graph as well, but the graph is a little more confusing. I'm going to go to Desmos, hit my keyboard, and then under functions. And by the way, on your other calculator, it's the same thing. Just go to math and hit the fifth option. And what we need is this right here, the nth root of a number. So we don't know what the root is, so we're going to put an x right there in the index. And then we're going to put in the number 700 or 7,776. Got a nice graph over there. That's not what I'm going to be looking at. What I'm going to look at is the table in just a moment, but I'm going to put in the second number, which was 216. I'm going to go the same process, which is to go miscellaneous. There's the nth root. We don't know what the root is. That's what we're searching for. And then we type in the number 216. All right. So what we're going to do is look at the tables and see where we have integers. For instance, obviously 7,776 to the 1 power is a perfect root. And I'm going to just hit enter a few times until I see an integer. 6 to the 5th power. So that's what this one is, 6 to the 5th power. So there's a base of 6 that can get me 7,776. Now, there may be more, but why not take a look and see if 216 also has a 6? So I go to 216, here's the table, there's 216 and 1, obviously, and there is the 6 with a base of 3. So what I've learned here is 216 is 6 to the 3rd power, and 7,776 is 6 to the 5th power. So this is how we can use our Desmos or a graphing calculator to find these bases of these numbers that are just really hard to find. So there you have that. That will be on your Canvas page if you want to go back and look at those. But like I said, we just learned that 7,776 is 6 to the 5th power. That is that. And we learned that 216 is 6 to the 3rd power. Just like that. Now I'm going to put the other two things, the other exponents back up there just because they can't just disappear, right? So this is this and this. And by the way, what you just learned on the graphing calculator can be used on the easier, smaller numbers as well. You can use that same thing on the smaller numbers. So the 6 bases are going to cancel. If you want to do your distribution where they sit, some of you are pretty good at doing some mental math on that. You can do that as you transfer these down. That'd be 5x plus 25, and this one would be 9x plus minus 15, excuse me. But I don't want to skip too many steps at one time. We got a lot going on here. So we go here, and we are going to distribute. Both sides have distribution. Doesn't have to be true, but it can be. So this is 5x plus 25. And this is 9x minus 15. Keep on working our way through this. Minus 4x. At this point it should be familiar. And I'm going to move the 15 over in the same step. I like to do that. We're kind of next level on these, so we can do that. So this is 40. This is 5x. We divide both sides by 5, and we get an answer of 8. Now, if I had my Desmos still pulled up, another advantage to this, these two equations should be crossing each other at x equal to 8. I don't know if we can see the 8 in that video there. Whoops. See if I can pull that video and see if 8's in the shot. Whoa. Okay, not going the way I hoped. Anyways, if I were looking at my Desmos, they should cross at 8. Again, it's really hard to see that sometimes, though, because the lines are not generally, they're always asymptoting, but sometimes it's asymptoting, so it's hard to tell where those lines actually cross. So the table would probably be a better place if you graph those two, this part right here. If you were to graph these two parts, you would see where they crossed. Which you could do that from the beginning as well, but I want to see your work. So give me those.